we'll continue where we stopped in the last lecture about brakes aspect. The learning outcomes for today's lectures, we are going to understand the drum brake system. Already working method is covered and types also covered. Even then I will give a brief information about the types aspect. Then we move on to brake torque requirement. Okay, particularly we are focusing about internal shoe expanding brake aspect. And I'm sure you know this is the typical schematic diagram about the internal shoe expanding brake or drum brake. When you say internal expanding shoe brake, so the shoes are arranged inside the drum, right? You can have outside also, depends on the application. In automobile, usually the shoes are arranged inside the drum, and the moment you have a force activated through wheel cylinder, right, the shoes will try to move to make a contact on the drum. So that's why it's called internal expanding shoe. Based on this arrangement, again you can have various classification, and you can see this. It's a very nice internal expanding shoe brake. In fact, this is actually you can see only one wheel cylinder. Then you have the adjusting thing. It's a leading and trailing shoe brake. Okay, this is a leading and trailing. We'll discuss what does it mean leading, what does it mean trailing aspect. And this is again the complete assembly of a drum brake system, where you could see this is a brake drum cover, and this is a hold down spring to holding the entire the brake shoe arrangement, and on top of it will be sitting onto the brake adjuster, and this is your wheel cylinder. Hope you remember yesterday in the one of the sample demonstration I have explained about the bleeder valve aspect, where when any leakage is there, any trap, air trap, that has to be removed, right? That's the purpose of having a bleeder valve. And this is the brake line where the brake fluid goes inside to activate the cylinder for the activation port or on the tip of the shoes. Okay, and based on the arrangement, so drum brake can be classified into 4 different aspects: a leading trailing shoe brake, 2 leading shoe brake, S-cam, duo servo shoe brake. I'm sure you would have seen the videos. Nevertheless, we'll explain about the first 2 arrangement: leading trailing shoe brake as well as leading 2 leading shoe brake aspect. And you could see that this is a leading trailing shoe brake. Okay, this is a type of brake is equally effective for forward as well as reverse braking, offers a stable braking force. In general, it is used most often as a rear brake in passenger vehicle. That's true. Always the drum brake are preferred to fix at the rear rather than the front axle. The front usually the disc brakes are arranged. In fact, if you see why this is called a leading and trailing shoe, right, we'll explain about. So this is the leading shoe, local. Okay, this you could see this is a drum rotation, right? So what is the friction aspect? The friction on the drum direction would be opposite to the rotation. So this is your friction, right? This is the drag or friction, something like that. We can say that this is drag on the drum. This is on the drum. Okay. So this is moving, right? This is happened. Now, what do you expect the friction force on the shoe? Should be opposite of that, because that's the one is going to make, and you have to balance the forces. Okay. Now, this is the where the wheel cylinder will come and will give the, this is the your activation force. This is activation force. Let me ask a simple question. If your drag force and activation force are the same in the direction, what is the effort of braking? Would be easier or tough? Right. So maybe I'll give another two example. You are moving on the road, so your friend also moving on the road on the same direction. Which is easier, if he moving on the same direction, pull him off, or if it's opposite direction? Opposite direction, where you need to have more force to stop him, right? Whereas the same direction, then the effort will be very less, right? Very less. So in fact, this is moment, okay, so the moment of frictional drag force along the shear input, okay, which is happening. So thus the increase in input load increase the friction drag force, and finally this is called self-servo effect. It's called self-servo effect or self-energizing effect. This is the arrangement if you have a leading shoe. The frictional force and the activation force are in the same direction. The braking effort will be braking effort will be good with the less effort. That's the difference. Okay, that's why this is called a leading shoe. Then when you go for the this is excellent for a braking effect, true, and this is the trailing shoe. So the drum is rotating, obviously the drag force will be in this direction for the drum. This is drag for the drag on the drum, okay, and obviously this is to balance the force, the friction force acting on the shoe will be opposite direction. This is, you can see that, and this is the activation force, and take the moment, what happened, that would be opposing the things, that would be oppose the shoe input load. So what happened if you have opposes the shoe input load, okay, so they thus increase the input load, decrease the drag force, obviously further reduce the braking effect, further reduce the braking effect. This is what happening when you have a trailing shoe. Okay, you may ask another question, what happened if you have reverse direction? How do you expect in the reverse direction? The leading shoe will be a trailing shoe and the trailing shoe will be the leading shoe. Okay, so it will change. Okay, so to avoid that, you can have another wheel cylinder at the bottom. So the two wheel cylinder, so any given time both leading and leading, you can do the arrangement. By doing that, the braking effort would be much better, right? And maybe you can see here, this is the, in fact, and this is the shoe arrangement. So the trailing shoe, you can see this is the your friction material, right? This is your friction material, and for trailing shoe, the area wise, right, the friction material is less compared to a trailing shoe. Obvious, because your braking effort already better if you have a leading shoe, then you don't need to have a more frictional material to create the braking effect. So in fact, by looking this arrangement, you can easily identify which would be the leading shoe and the trailing shoe also. But this is based on the leading and trailing. How about if you have two leading? Then the size of the brake lining would be equal. You can't able to find out the differentiation. This is difference can be able to find out only if the brake arrangement is the leading and trailing aspect. Okay. Now we are talking about two leading or twin leading brake system. You could see that. So we have two wheel cylinders, right? Two wheel cylinder. So when one force is acting from one wheel cylinder, right, the same wheel cylinder acting another way. So what do you expect? You would expect two leading aspect. During the forward movement, the vehicles both shoe act as the leading shoes and providing a superior braking force. This type of use where such a strong force required mainly in truck and other commercial vehicles. Wherever you have a large vehicles where you need a more braking effort, there you could have twin or two leading shoe arrangement. In fact, in the demonstration, a stage demonstration, I have shown the two leading, right, You have seen the two leading, I mean instead of two leading, two cylinder drum brake, you would have seen that, the bigger one and smaller one. So both are used for trucks and heavy commercial vehicles. You can see that. So by looking at, if you have, this is the wheel cylinder 1 and this is another wheel cylinder. So there is no adjustment screw. At any given time, right, both shoes would be a leading shoe, so that you would have a better the braking effort, right. The brake torque analysis. Now we will understand about how the force activated, how the torque applied, and when it say torque, it's a frictional torque, and for drum brake analysis, right. So these are the following assumption we are exclusively used for automotive application. Drum brake, I am talking about a drum brake aspect. Compact and economical. Brake shoe, one end pivoted, another end is subjected to activating force. That is true. Okay. Then assumption, before deriving the equation, this is the following assumption we need to consider. The intensity of normal pressure distributed between the friction lining and the brake drum at any point is proportional to vertical distance. This is the assumption we had to have. That is one assumption. The second one is the brake drum and shoe are rigid. The centrifugal force acting on the shoe is negligible. More importantly, the coefficient of friction is constant. Obviously, friction is variable due to temperature, right? Variable due to temperature. So what I am going to do, so I will just show a schematic diagram, okay. I draw the circle. This is for the drum aspect, right. This is drum aspect. So drum is pivoted at the middle, right. So drum is pivoted at the middle, okay, and assuming that is rotating, so in this direction. So when it is rotated, right, R is the radius of the drum, R is the radius of the drum, okay, and the lining where it starts, that position to till there we can say as a theta. Then, right, so you would expect two things. One is your normal force, right, we will take this small dn, and the since is against doing with the friction is the frictional force. These two things are operating. This is on the drum, okay, this is on the drum. So let us see for the shoe also, right. On the shoe arrangement, just I wanted to show the shoe alone. Right. Yeah. So the radius is R, that already you know that. This is the radius is R. Usually shoe will have a pivots, right. This will have a pivots, then it moves like this. Okay. Then I am just showing only one aspect. Then the activation force will be in this direction. P is the activation force, and then we will have friction material. Friction material. This is your friction material. Right, this is your friction material. The angle, right, where it start to end is the theta. Okay, this is theta. We will discuss in detail, and the distance from the pivot to where the activation force start, we say as a c. Length is a length. Then from the center of drum to, okay, the center of the pivot, this distance called taken as a h. This is taken as h. Right, this just giving a description about the shoe arrangement in the drum brake, okay, and this is shoe, right, okay. Let me ask, what is the forces act on the shoes now? It will be what are the forces acting on the drum? Same force will be in opposite direction, right? Right. We will have a in this direction mu dn, and in this you will have a normal force dn. These two will happen. In fact, I'll go in detail more. Maybe you could see the free body diagram. You can see the complete information, right? So the complete information you could see here from the pivot to where activation force start, the distance already I have mentioned. Then from the center of the drum to and the pivot, the horizontal distance h is mentioned. Okay, and this is the radius of your drum, r is given. Then where the friction lining starts, right? From the pivot to where friction lining start is a theta 1. It's a theta 1. Then where the friction linings ends, right? From the pivot to theta 2. Then the theta would be theta 2 minus theta 1. So that is your arc length of the brake lining, right? You could see that is the arc length of the brake lining. In fact, to further understand what we do, we will take a small strip. This strip alone we will take it, right? This strip alone take is a d theta, assuming that, yeah, d theta. Then try to do the force balances. This force balance I already said there are two forces. One is normal force, another one is frictional force. These two forces are going to act on the shoe. Okay. Since the rotation is there, obviously we are talking about the friction. You can see that this is your friction in this direction will come, right? Then the normal would be in this direction, right? Normal would be in this direction. So this is the free body diagram. Hope you will understand that. So what I am going to do, I am not due to time constraint, I am not going to detail. You can refer any textbook where the complete information is given. It take another 2 lectures to complete derive the equation to understand. So instead that, what I am going to do, I will straight away give the equation and proceed further. Okay. So what happened? Let me check. So always we will take the moment. When they take the moment with respect to pivot acting on the tip, that is normal, right? That is one thing. The another one is frictional moment. Which is the responsible for torque? Friction, right? Frictional torque. So these two things we are going to right straight away get the equations. Yeah, the total brake torque equation. The total brake, right? I'll make it as a MT, right? MT. This is general equation. This is mu equal to mu dn r, right? If rewrite in a very proper way, mu w r square, P max is the pressure, sin theta max, then integration theta 1, theta 2, sin theta and d theta. If rewrite, so straight away after integration mu w r square, P max sin theta max, right? This would be cos theta 1, cos theta 2. So where the W is the width of friction lining, width of friction lining, width of the friction lining. So this is about the total brake torque equation aspect. Now we will find out for the moment of normal pressure Mn. Again the moment of normal pressure Mn is the standard equation dn h sin theta. Okay, the standard, from there we can get it as a w or h p max sin theta theta 1 to theta 2 sin square theta d theta. This is the equation. So once you substitute, finally Mn would be arrived as WR H P max theta 2 minus theta 1 minus of sin 2 theta 1 2 sorry sin theta 1 divided by 4 sin theta max. This is the one. So in fact the limits, just wanted to show the limits. When theta max equal to 90 degree, right, theta is a max 90 when theta 2 greater than 90 degree, that means talking about the shoe lining aspect. When theta max equal to theta 2, that itself, then straight away when theta 2 less than 90. So these are two conditions we always use for solving the torque equation of brake drum. Okay. Now we will go for the actual aspect. So we derive the equation. Okay, we derived for the moment of normal pressure and also the moment of frictional torque as well. Both we have done that, right. Now we will take it as a activation force. Remember, this is your drum, right, and this is your shoe arrangement. Okay, so from here to here, this is the P and this is your distance C. Okay, you take the pivot with respect pivot moment when applied force here, right. So what do you expect the equation, right? I think I might have it here. Yeah, for a clockwise, then I think let me check. Yeah, you would expect P into C plus Mn minus 1 minute should be M minus Mn. I am trying to balance it, right? So the P into C act as a couple. P into C act as a couple. Then in clockwise direction, that's what we assumed. So when you make it very simplistic way, P into C equal to Mn minus Mf. Finally, if you want to understand, to find what would be the activation force, Mn Mf by C. This is the equation you are expecting. Okay, this is equation is for leading shoe or trailing shoe. What we have done is for a leading shoe aspect, for a leading shoe, right. The braking effort will be very less. Suppose for trailing shoe, what do you expect the brake activation force would be more or less? See, the friction force change the direction, right? The friction force will changing direction. So obviously P equal to Mn plus Mf, right, Mn Mf by C. So you can see that this is adding, Mf is adding to your trailing shoe. That means the braking effort will be very less. You have to have a more effort. So this is for the trailing shoe aspect. This is for trailing shoe aspect. Okay, let me ask question. What happened when you do the reverse direction? What do you expect reverse direction? Yeah? What do you expect in the reverse direction? Yes? It will reverse. Okay, it will be reverse. It will be reverse. And I have to talk about, there is a concept called self-locking, right. So this is reverse. Okay, I'll ask one more question. What do you expect if my Mn equal to Mf? What happened then? There's a chance, right? There's a chance where the normal, right, force, right, the moment of normal force and the moment of frictional force are equal. What happened to the vehicle? It will be self-locking. It is called self-locking. When Mf equal, then it's called self-locking. What do you mean by self-locking? The brake won't be effective. The wheels will rotate freely and vehicle cannot move. Right, that's what happening. It's an instability. Right, so self-locking is nothing but instability. So that is not advisable. That's not advisable. We always try to have a difference in between the magnitude difference between Mn and Mf. Never ever design the brake such with it both are equal. Okay, that has to be taken into consideration. Yeah, you can see this. So in fact, clockwise rotation of the brake drum, Mn minus Mf by C, self-energizing effect. When the activation force P is 0, then you will have self-locking. If the anti-clockwise rotation the brake drum, then Mf direction change, which already I have discussed. Okay. Now we will do a problem. Okay. We will do a problem. You want to write the equations? Okay. Yeah. When we do the equation, when we do the problem, we will write the equation in detail again. Can you take down the problem, please? This is a very generic problem. Yeah, a Maruti 800 car weighing 1100 kg along with the passenger is moving on a level road at a speed of 65 km per hour. When the brakes are applied, the car stops in 4 seconds. The brakes are applied in all 4 wheels. The radius of tire is given 220 millimeter. If the weight of each brake drum assembly is 12 kg and specific heat capacity is 460 joules per kilogram degree Celsius. A. Determine braking distance. B. Total energy absorbed by each brake if kinetic energy of rotating parts is 10% of kinetic energy of moving parts. And C. Torque capacity of each brake. And D. Temperature rise of brake drum assembly. This is normal physics based problem. Okay. Even though the application is related to brake, to understand for you what exactly happening due to the physics aspect. So the data is given, the weight is given 1100 kg along with the passengers, the speed is given 65 kilometer and the car stops 4 seconds. That means that is your braking time. TB braking time is given 4 seconds. The brakes are applied in 4 wheels, so the radius of radius of tire is given 220 millimeter, and each brake drum weight also given 12 kg. Then specific heat capacity 460 joule per kilogram degree Celsius. So we have to find out the braking distance, total energy, right, torque capacity of each brake and the temperature rise. These are the things we need to find out. This is our first problem. Yeah. So we will find out the car velocity, right? This is the first problem, right? Car velocity is given. Car velocity given how much? 65 km per hour, right? 65,000 divided by 3,600 per hour. So that give me 18.06 meter per second. So that's a velocity. The braking time. What is the braking time? 4 seconds, right? TB, B suffix for braking time. 4 second is given. Okay. So this is the car is moving, right? Car is moving. So when car is moving, the initial velocity is a 65 kilometer. What is the final velocity? 0. V2 equal to 0. So that is your final velocity. Yeah. So final velocity given. So we need to find out the distance traveled, right? Braking distance we need to find out. So distance traveled, yeah, S1. We'll take the, we have to take the average velocity, right? 0 velocity and then 18.06 by 2 into your braking time. So what is the answer you are getting? You should expect 36.12 meter. So that is your braking distance. This is your braking distance. Okay. Then we have to find out the kinetic energy, right? The total kinetic energy, because we need to find out ultimately the energy absorbed each brake, right? Energy absorbed each brake we need to find out. So car weight is given W, right, 1100 kilogram. Okay. So change in kinetic energy, what will be the change in kinetic energy? I am talking about change in kinetic energy of the vehicle, of M2, right, V1 square minus V2 square. .06, this will be 0. So can you tell me what is the answer you are getting? Are you getting 1799, right? Sorry, 179.39 kilonewton meter. This should be the change in kinetic energy of the vehicle. Okay. Just I wanted to inform you, right? When this car is moving, the car is moving in straight direction. The car is moving in straight direction. What happened? The other parts inside the car. When the car is moving, it's a translation motion, right? It's in a translation motion. But there are components, we have a rotational movements also. They have rotational movements. What are they? Your flywheel is a rotational movements. Your clutch is a rotational movement. Okay. Not only flywheel, clutch, your entire gearbox. The gears are rotating rotational movement. Okay. So then wheels, your brake wheels, your tires also rotation motion. So in fact they are also carry the energy, right? So that you have to consider. So that is the precise reason they said kinetic energy of moving part you can usually take it in the percentage wise, maximum 20%. It varies, depends on the size. So 10% of the vehicle you can assume as for the moving aspects. In fact, when we do a problem, we have to find out precisely how the moving parts kinetic energy would affect the brake performance. As we move on to the lectures, we will understand that aspect as well. So the kinetic energy of the vehicle, kinetic energy of moving or rotating parts, both are same, moving parts should be 10% of, right, vehicle is given, right, 10% of the vehicle is given. So that should be 17.939 kilonewton meter. Then the total kinetic energy kinetic energy of the vehicle plus kinetic energy of your moving parts. 179.39 plus 17.939. Okay, I should expect 197.329 so much kilonewton meter. This is the total kinetic energy of the entire vehicle. Alright. So what was the question asked? What was the question asked? They asked energy absorbed by each brake system, right? So energy absorbed by each brake system. So when you want to have energy absorbed by each brake, so what do? How many wheels are there? How many brake system? 4. So divided by 4, that should give 49 point, right, 32 so much kilonewton meter. This is the for each brake system energy EB per brake. So this is the answer, you should have it. Right. Yeah. Now we need to find out what is the next question? Torque, right? Yeah. What is the next point we need to find out? Torque capacity. Yeah. So how are we going to do? Find out the torque capacity, the basic physics equation. So you have energy is given. So what else we need to find out? We need to find out the MT. We have to find out the MT, right? But we know EB is given. Already we know the energy also. So how can we do the? How can we able to find out MT? Torque into angular, right? Can we say angular rotation, angular acceleration? What is that? Angular velocity. Okay. If you do that, can you able to find out the torque, right? So in fact, your EB equal to MT into theta, radians. Angular rotation is given. Okay, so we need to find out the theta value. What is the value, right? And we know V equal to what? R omega. R omega. So R is the radius of the wheel or tire. Either way you can see that. The speed we need to know that. Yeah. So can you find out what will be the theta, please? Yeah. This we have to use the equation. Theta is nothing but the sliding distance, yes, what we found out. From there your radius of the wheel. So you have to use these two equation to find out the V and theta. Okay. Can you find out, please, what is the value you are getting? What is the omega value first? The omega value V equal to 18.06, right? R equal to 0.22 decimeters. Okay, that should give me 82.09 radian per second. So the radian per second omega I have. Then another thing is I need to find out the radian theta, which is nothing but S equal to what? 36.12, right? And this is R equal to 0.22. That should give me 164.18 radian. Radians. I have all these things. So then MT equal to 49. 49.332 so much 10 power 3 will make it as a Newton meter divided by your 164.18. The torque capacity would give me 300 Newton meter. This is the value you should expect. Okay, this value you should expect. Now, the another one, temperature rise, right? So, energy equal to cooling law, m into what? Cp into delta T, that is it, right? M into Cp into delta T. So, we need to find out the delta T, right? So, E equal to mCp, right? So, this will be 49,332. Yeah. What is the m here? Brake, weight of the brake, okay, 12. Then specific heat capacity given 460. So, when you do that, so the temperature rise due to the braking thing is 8.94 degrees Celsius. The delta T 8.94 degrees Celsius. This is the thing. Okay. Yeah. So, that is fine. We will move on to the one more problem just for you to understand. Yeah, this is the another problem. This is okay. A four-wheel automobile has a total mass of 1000 kg. The moment of inertia each wheel about a traverse axis through its center of gravity is given as a 0.5 kilogram meter square. The rolling radius of the wheel is given as a 0.35 meter. The rotating and reciprocating parts of the engine and the transmission system are equivalent to moment of inertia of 2.5 kilogram meter square, which rotates at 5 times the road wheel speed. The car is traveling at the speed of 100 km on a plain road. When the brakes are applied, the car decelerates at the rate 0.5 gravity. There are brakes on four wheels, so you need to find out the energy absorbed by each brake and also the torque capacity of each brake. So, how does this problem is different from the previous one? What data do you have here? The mass is given 1000 kg, right? Mass is given, then center of gravity is given, right? 0.5 kilogram meter square. Then radius of the wheel is given 0.35 meter. Then moment of inertia of the rotating and reciprocating parts, right? It's given 2.5 kilogram meter square. And one more information is given, these parts will rotate 5 times on the road wheel speed aspect, that is clearly given, and speed also given, right? And instead of velocity, it's given as the car deceleration, gravity is given 0.5 g. Okay. So, how are we going to solve this problem? Yeah, I think similar way, right? Whatever you did, we did it in the previous problem. Same way you can do that. The only difference is you have deceleration. You have deceleration. Okay. I think I will stop now. I will stop here. So, you do the problem. Okay, we will discuss it on tomorrow lecture.